Hello, my name is Huntran. In this video, we're going to be taking a look at a flash calculation using Rachford-Rice method. And so we're going to be taking a look at a flash drum, and we're just going to derive the equation that we can use to solve for the liquid and the vapor and the liquid mole fraction and the vapor mole fraction coming out of a flash drum. So let's just take a look first at the flash drum and what a flash drum is, what it does, and what all we need to be calculating for. So we have a flash drum, and going into this flash drum there is going to be a feed, and this feed is a mixture, and it's going to either be all liquid, all vapor, a mix of liquid and vapor. But as it goes into this flash drum, it also has a feed mole fraction, and so how much of it is a certain component. Coming out of this flash drum is going to be liquid and vapor. So as it goes into this drum, it's going to separate into vapor and liquid, and then it's going to come out as vapor and liquid in separate pipes, and then there's going to be a vapor mole fraction and a liquid mole fraction. Additionally, we are given a set temperature and a pressure. And so what we know is we know the amount of feed going in, we know the temperature and pressure. What we don't know and what we need to look for is the vapor and the vapor mole fraction, the liquid and the liquid mole fraction. Forgot to mention we also know the feed mole fraction. So these are known and these are unknown. And so first, if we take a look at just the mass balance aspect of it, what goes in has to equal what is coming out. And so going in, there's the feed, and coming out, there's the vapor and the liquid. So the feed equals the vapor plus the liquid. And then each of those components, the feed, the vapor, and the liquid, they all have a mole fraction for that specific component of the mixture. And so feed times the feed mole fraction is going to equal, of one component, is going to equal the vapor times the vapor mole fraction of that same component plus the liquid times the liquid mole fraction of that same component. So this we know because of mass balance, we know those to be true. Another thing that we can establish is a ratio. There is a ratio between the liquid and the vapor mole fraction. So this is the ratio between the vapor mole fraction and the liquid mole fraction. Now, we can also refer to Raoult's law. Raoult's law is a topic that we covered in a previous video, which is the liquid mole fraction times the saturated vapor pressure of the component equals the vapor mole fraction times the total pressure. And so, using Raoult's law, we can also establish that the ratio is going to equal the saturated vapor pressure of the component over the total pressure, and this is just from the cross multiplication. So if we were to cross multiply, that would go there and that would go there. So we know that to be true. We can clean it up so it's not as messy. And so now we can begin with the Rachford-Rice method. So this method is used for problems with a vapor-liquid equilibrium. And so something that we know is that the summation of the vapor mole fractions minus the summation of the liquid mole fractions is going to equal 0. And we know this because the mole summation of the mole fractions of the vapor phase equals 1, and the summation of the mole fractions in the liquid phase also equals 1. So 1 minus 1 is going to equal 0. So that's where this equation comes from. And so if we were to simplify and clean it up a bit, we can get the summation of the vapor mole fractions minus the liquid mole fractions equals 0. And so this equation has two unknowns. So what we're going to begin doing is just using these equations that we established up here and maybe switching things around in a way that allows us to substitute our unknowns with our knowns. So to start, we don't know the vapor mole fraction, but we know that the ratio equals the vapor mole fraction over the liquid mole fractions. So if we move things around, the vapor mole fraction equals the ratio times the liquid mole fraction. So if we substitute that in, we have the summation of the ratio times the liquid mole fraction minus the liquid mole fraction equals 0, and then we can clean it up and have the summation of the liquid mole fraction times the ratio minus 1 equals 0. And now we have this liquid mole fraction, which we also do not know, but up here we can use this equation. And so we have the feed times the equation that states, it was a mass balance equation that states that the feed times the mole fraction of the feed of component I equals the vapor times the vapor mole fraction of component I plus the liquid times the liquid mole fraction of component I. And so these are both known, so we can keep that as is. Again, we don't know the liquid mole fraction, or the vapor mole fraction, but we have that up here that we can substitute in, which is how we substituted it on the left here. We can just do the same substitution. So that's going to give us the feed times the feed mole fraction of component I equals the vapor times the ratio times the liquid mole fraction plus the liquid times the liquid mole fraction. Now we also don't know the liquid, but another one of our mass balance equations is the feed equals the vapor plus the liquid. So if we move things around, we know the liquid is going to equal the feed minus the vapor. So we can plug that in as well. And so that's going to give us the feed times the feed mole fraction of component I equals the vapor times the ratio times the liquid mole fraction plus the feed minus the vapor times the liquid mole fraction. Now what we can do is we can distribute out the liquid mole fraction, so that's going to give us the feed times the feed mole fraction of component I equals the liquid mole fraction times the quantity of the vapor times the ratio plus the feed minus the vapor. And now we can isolate the liquid mole fraction, and that's going to give us the feed times the feed mole fraction component I all over the vapor times the ratio plus the feed minus the vapor. And now we can begin cleaning things up. So we can distribute out the vapor, so that's going to give us the feed times the mole fraction of component I of the feed over the feed plus the vapor times the quantity of the ratio minus 1. And now we can continue to clean it up and divide everything by the feed. So that's going to give us the liquid mole fraction equals the feed mole fraction of component I divided by 1 plus the vapor over the feed times the ratio minus 1. And so if we use that and plug it in to the equation here on the left, we will have the summation of the feed mole fraction times the ratio minus 1 all over 1 plus the vapor divided by the feed times the quantity of the ratio minus 1 is equal to 0. So we know the feed mole fraction, we know the feed, and we know the ratio because the ratio is the saturated vapor pressure over the total pressure, and we can find the saturated vapor pressure because we know the temperature, so that's just Antoine's equation, and we are given the pressure, and so we know the ratios as well. And so the only unknown we have is the vapor. But we have one unknown and one equation. So we can solve to give us the vapor, and then once we have the vapor, we can use that to solve for the liquid mole fraction, and once we have the liquid mole fraction, we can use that to solve for the vapor mole fraction, and once we have the vapor mole fraction, we can use that to solve for the liquid. And so by finding the vapor, we are able to solve for the mole fractions as well as the liquid. And so although we do have an unknown remaining in the equation, this is the equation that we can use for the Rachford-Rice method to solve for the vapor, the vapor mole fraction, the liquid, and the liquid mole fraction. So that is the final equation that we have derived.